It's a pleasure to present our speaker, the first speaker of this year's seminar session in geometry and physics. Is B.Shapiro from originally from Moscow and now from Stockholm University.
Thank you so much. It's a real pleasure to visit your nice country. It's my first time, hopefully not the last one. And so this is more like a colloquium type of talk, and it wouldn't be very technical. I want to present some rather surprising piece of literature and statements I found by chance, completely by mistake, in a well-known book by James Maxwell, published in 1860s, where he claims something very strange, and he provides it with a proof which actually involves a piece of mathematics which was developed only in the beginning of the 20th century, but also his proof is completely wrong, although very interesting. And I'll tell you what we know nowadays about this topic and how little we know about this topic. And the topic is as follows. So these are the main references. I'll leave this file here, and you are very welcome to take a look. And the problem is as follows. I'll formulate the general n-dimensional problem, and then we'll try step by step move in dimensions. So it's about Newton potential of a configuration of fixed point charges. So Newton worked on this kind of thing in his Principia in the 17th century. But the problem I'll be discussing is as follows. Assume that you have a bunch of charges, or bodies if you want, point masses, which are nailed in some positions in the space, can have different masses or charges, and they create the electrostatic field, the gravitational field. So when you have a unit mass which is moving in this field, attracted by these different masses, fixed, and you are trying to understand how many equilibria positions are there. For example, the trivial example is if you have two fixed point masses, and then definitely there is one equilibrium position on the line connecting them. So this attracts on one side, this attracts on the other side, and somewhere in the middle these attraction forces cancel each other, and you have a unique equilibrium position in between. But now assume that you have a bunch of charges in three-dimensional space. Then you want to count how many such equilibrium points, equilibrium positions are there. So mathematically, this is about each point charge, say of value xi, creates a potential function. So you can, instead of looking at charges, you can look at potentials. So each individual guy creates a potential like this, depending on the dimension. And in the two-dimensional case, it's a special situation. You have a so-called logarithmic potential. And now you add these potentials from each of your individual charges, and you want to understand how many points are there where the total potential has gradient vanishing. So that's our general problem. So say we're giving L positive and negative charges. We can specify how many positive or negative are there if necessary. And we want to estimate from above what's the maximal possible number of points of equilibria for such a configuration, depending on the number of charges and the dimension. So the classical case of this thing was actually solved by Gauss. In his Gauss published 1/5 of what he knew. And in his Gesammelte Werke, in one of the volumes, he has the following statement that in the plane where we work in the so-called logarithmic potential, this is a very special situation closely related to functions in complex variables, which makes everything much easier. So the potential of a configuration of charges placed at the positions Z1 through ZL and such values, you get such a total potential. And Gauss observed that the gradient of this function up to complex conjugate is the same as the derivative, complex derivative of this function. And if you differentiate this function, you get a rational function like this. And obviously, if you now you have to look at the numerator, you can expand it and look at the numerator. The numerator would be a polynomial of degree at most L minus 1, where L is the total number of points. And you can conclude that the number of points of equilibria would be the same as the number of zeros of this rational function. They would be at most L minus 1 of them, and all of them would be saddles. So that's a very easy situation. And typically, if you perturb your points and your charges a little bit, the total number of equilibria counted with multiplicities will be the same, would be L minus 1. And this is an easy and nice situation. So unfortunately, or I don't know, maybe fortunately, in dimensions higher than 2, life is not that easy anymore. So let's assume that we have in n-dimensional space, when n is at least 3, mu plus nu fixed charges, that many positive and that many negative. Now they create the electrostatic field like this. And we want to find how many, we want to find effective bounds on the number of critical points of such a function, which looks like a simple question, but it isn't. Now let me observe, first of all, that in general, points of equilibria for systems of point charges don't have to be isolated. So the simplest situation is like this. Take in the three-dimensional space a square and put the charge +1 here and -1 here. Then it's an easy calculation that if you look at the line through the center of the square perpendicular to the square, it will all consist of equilibria points. But such situations is rare. If we perturb our configuration a little bit, immediately all points of equilibria would be isolated, and in what I'll be talking about, we assume that points of equilibria are isolated and moreover they are non-degenerate, which means that the quadratic form close to each of them is a non-degenerate quadratic form, the quadratic part of the potential, which is the situation of general position. I want to mention in connection with this the following extremely irritating thing, which unfortunately is still open and nobody really knows how to approach this. In this toy example I mentioned with a square, where points of equilibria form curves, we have 2 positive charges and 2 negative charges. And one thing, assume that we have charges one and the same sign, say masses. So it looks very natural that if we just have masses, points of equilibrium will always be isolated. They cannot form continua, but this is completely open. One doesn't know how to approach this kind of thing, although it looks extremely natural. Okay, now who worked on this kind of question? So first, when I don't know why I started thinking about this problem, this was maybe 15 years ago, but I found some references quite easily, because Marston Morse, who was the famous American mathematician, the developer of Morse theory, which is a study of topology of manifolds in terms of nice, smooth functions on these manifolds. He started with the problem of geodesics on the sphere and developed his Morse theory, and he in particular, after the war, he was thinking about this question. And even in the 30s, I think, he first studied it. But the material I'm presenting is in his book, which is from the 60s. Morse theory in general is oriented towards estimating the number of critical points of certain functions from below, not from above. But in particular, he proved the following thing. So, this is the case, this three-dimensional case, yes? So assume that we are looking at, in the three-dimensional spaces, we have a collection of L charges such that which could be both positive and negative, and assume that the total charge, in other words, the sum of the charges, is negative. So in three-dimensional space, a potential is a harmonic function, which means it does not have maxima or minima. It can only have critical points of index 1, or assume non-degenerate, and critical points of index 2, which, if you don't know, means that if we look, so at the critical point, the gradient of our function vanishes, and the quadratic part of our function is a non-degenerate quadratic form. If it has one negative, so you can reduce it to sums of squares, or whatever, squares with signs. So if the number of negative squares is 1, is a critical point of index 1. If the negative point has two negative squares, it's index 2 critical points. Okay, now he has shown, and we can also, I'll try to reproduce how the proof goes, is that if the total charge is negative, that the number of critical points of index 2 is at least the number of positive charges, and the number of critical points of index 1 is at least the number of negative charges minus 1. And the sum of the number of negative points of index 1 and 2 is mu minus 1, which is a constant. It does not depend on how many points of index 1, how many points of index 2 you have. Okay, and there is a generalization of the statement to the case of dimension bigger than 3. And in this case, you have to count points of index 1 and point of co-index 1, or index n minus 1. And it looks similar. In any case, you have the following, except this relation for the Euler characteristic, which is the difference between the number of critical points of index 1 and 2, you also have the upper bound for their sum, the lower bound for their sum, which is like this. So the sum of m1 plus m2 is at least the total number of charges L minus 1. So such configuration actually exists, and they are called minimal, and they occur in all dimensions if you align all your charges. If you put your charges on a line, so you'll get some number of critical, you typically get, so assume that here I am in 3 dimensions, but I'm very naive and putting all my charges on the line. So in such situation, all the critical points will still stay on this line, and they will be one less than the number of charges. That's a very simple situation, easy to study. But when the dimension is at least 3, there are configurations which are not non-minimal and stable, meaning that if we perturb our charges and the locations of our charges and the values of the charges a little bit, the number of points of equilibrium will still stay the same. Let me show you what one thinks happens in 3 dimensions, just to illustrate the situation. And we'll use this, my picture, a little bit later on as well. Okay, so assume that we're in the simplest possible situation. We just have 3 charges in a 3-dimensional space. Now, first of all, we can more or less restrict our consideration to the plane which is spanned by those charges. Because, so say we have 3 points in 3-dimensional space. First of all, a simple observation is that we can restrict our consideration to the plane spanned by these charges, because off this plane, the gradient or the gradient of the potential cannot vanish. So all positions, equilibrium positions, if they exist, they should sit in this plane. Okay? But now I am saying that typically one expects 2 different situations. If those 3 points are aligned or close to one single line, then what we have is the following. So if they are close to being on one single line, then our potential restricted to this plane would be like 3 large hills going up, and then we'll have 2 saddle points, one here and one here. So typically we assume that we can guess that we are in this situation like this. We have 3 charges on the line and then 2 saddle points for this potential, like this. On the other hand, if we now assume that our charges are close to the equilateral position instead, so we are in the situation like this. So we have 3 large hills close to these 3 locations. And now, so assume that you have 3, you are in the mountains and you have 3 hills located approximately as the vertices of an equilateral triangle. Then you have 3 mountain passes, one here in between these 2 guys, one close to here in between these 2 guys, and one close to here in between the remaining 2 guys. So just try to imagine this mountain landscape. But also you have a small lake in the middle. So the water will go down here and sit in here. So the number of equilibrium points, okay. Okay, sorry. So in this situation, the number of equilibrium points would be 4. And if you perturb your, how high your hills are and where they are located, it will still stay 4. So this is also, if 2 is a stable answer, if you have 3 hills, one behind the other, if you perturb them a little bit, you'll still have 2 mountain passes. And if they are like here, then you have 4 critical points typically, which will not go away if you perturb them a little bit. So But then by some, I don't quite know how so Professor Eremenko pointed me in the direction of Maxwell's famous book. It's called the Treatise of Electricity and Magnetism. It was published in 1860s. And the first volume contains Maxwell equations and a lot of very interesting mathematics. And the second volume is about electric motors and very technical engineering stuff. So he was a very surprising scientist. So by pure luck, I found a very funny statement in here. So he claims that in situation, if we have L charges independent, whether positive, how many positive or negative, doesn't matter, the total number of points of equilibria is assumed non-degenerate. So we are avoiding situation with continua, should be at most L minus 1 squared. So in this case of 3, so L minus y squared would be 4. So that's what he claims. So that's the picture I tried to explain to you. So if we have 3 charges close to a line, then we have, this would be a kind of geodesic map. So this would be this high mountains, and we'll have 2 mountain passes. And here, if they are close to the equilateral situation, we'll have 1, 2, 3 saddles and 1 minimum in between. So that's, according to Maxwell, this would be a complete description of all possibilities for 3 charges in 3 dimensions. Okay, but so even to prove this, even this claim is still open. So I'll tell you what we were able to prove with my co-authors, one from Weizmann Institute, another one from Purdue, some 12 years ago now. And our result is a little bit more general than the setup of Maxwell's conjecture, but it's incomparably, it's so far from Maxwell's conjecture. So we are still trying to improve it, but no real progress. Okay, so our setup is as follows. So we decouple. So potential in the n-dimensional space, as I mentioned in my first slide, it's in the form the potential of a single point of size psi. It's psi divided by r power n minus 1, where n is the dimension. But let me assume that I have a family. So the charge is here, but here I'll put a parameter alpha, where alpha is a positive number. But alpha is no longer related to the dimension of the space we work. And I'll be using this as a parameter. I'll be fixing a configuration of points, and I'll allow myself to increase alpha to show my results. Okay. So capital N will denote, so n would be the, lowercase n would be the dimension, this would be the number of charges, and alpha would be this parameter in the potential I'll be using. So in this
Is that alpha or 2 alpha? Because on the last slide, it looked like you had an extra 2. Is it 2 alpha in the experiment? Or is it alpha?
Yeah, 2 alpha. Yeah, 2, but it doesn't matter. Yes. Okay. Mm-hmm. So it will not affect the final answer. Okay. Anyway, this capital N would be the maximal possible number of critical points of such a potential with L charges, and will only allow non-degenerate configurations. So we'll assume that we're taking almost all configurations, because for almost all critical points would be finitely many, and they would be non-degenerate. Okay, and here is the result, saying that you can get an upper bound which only depends on L, would be independent of N or alpha, but that's a completely horrible number. Even for N equals 3, instead of 4, you get 12 digits. But I'll explain how we got this thing. It's from the general machinery of the so-called phenomenal theory, which was a very popular topic some years ago. But when we applied, instead of general results of this machinery, the tools of this machinery, so we were able to improve the situation with the 3 charges in an n-dimensional space, and for any alpha up to 12. Maxwell is 4. But this is about 25 pages of work, this particular thing. This, on the other hand, follows from the general machinery, which I'll tell you a couple of words about, because it's useful in many, many aspects, this phenomenal theory. And we thought of getting from 12 to 4, but so far we don't see a good clue. Technicalities are quite involved. Okay, now let me tell you some couple of words about what phenomenal theory is about. So it's about, every mathematician once in a while has to look at systems of m real polynomial equations in m variables, and everybody knows that you can estimate the total number of real solutions, in this case by taking the product of the degrees of the equations, the Bezout formula. Now, in many applications you have a little bit more general situation. You have polynomials in your variables, but also in the exponential functions in your variables. So the setup of a phenomenal system is as follows. So you have m real variables, and you have m equations, which are polynomials, but polynomials in the u's, but also in exponential. You take a linear form with real coefficients in u's and take e power. So these polynomials will depend on more variables, m plus k. You have m variables u's, and you have k variables which are double u's and which are some e power linear forms in u's. And in such situation, you are interested in counting real zeros for such a system. I just want to point out that if you want to count complex zeros for such a system, there will be infinitely many, because you have exponential functions involved. But in this situation, the number of real zeros is finite, and it's bounded by such a constant, which is due to Professor Khovansky himself. It was improved a little bit since he published his book in late 80s, but it has an exponential factor here. Nobody was able to get a polynomial bound, and apparently it's impossible. But it's still a fairly nice bound. So, and in our situation, we can rewrite the equations introducing some natural variables. We can rewrite our system of equations that the gradient of the potential function vanishes in terms of phenomenal system, and then just apply his result, and then we'll get this mess like this. But then the second result is technically much more involved, and unfortunately I don't have time. If anybody is interested in details, I'll be happy to provide. I'll be here tomorrow as well. Okay. Now let me also tell you about a conjecture, a result in the conjecture, which I think is nice, where we did the following. So if you fix a system of points and charges, but you are looking at the family of potentials associated with a fixed configuration of points and charges when you allow alpha to be a parameter. And it turns out when you increase alpha, you get into a very nice stable situation where you can really easily read off the number of critical points and the indices, and also associated to the so-called Voronoi diagram, which is a fairly classical notion appearing in many places in computer science, among other things. Okay, let me tell you what a Voronoi diagram of a configuration of points is. Voronoi was probably the first Ukrainian mathematician worth mentioning. He lived in the late 19th century. Okay, so what's a Voronoi diagram of a configuration of points? I'll draw the picture in the three-dimensional space. So assume that you have a collection of points in Rn, and you'll stratify the whole space according to what is the collection of, among those points, of those which are of the closest distance here. Okay, so let me see if I can manage to draw a reasonable picture. I know what to do in the, let me start with the case of three points. There I definitely know what to do. But then maybe we can experiment with a little bit more points. So say these are my fixed points called sites in this thing. And now I'm saying I'm looking at a variable point here, and I'm choosing what is the nearest, or what are the nearest points to my point. And I'm making a cell of those who have one and the same collection of nearest sites. Okay, so here in the case of 3 points in the plane, what happens would be the following. So I'll be getting such a situation. So this would be the unique point where all three of them are in the same distance, yes? So along this ray, these two would be the closest. Along this ray, these two would be closest. And along this ray, these two would be closest. So this equals that, this equals that, and this equals that. So my plane will be split into 1, 2, 3, 4, 5, 6, 7 pieces. 3 two-dimensional, 3 one-dimensional, and a point. So this is this Voronoi decomposition of the plane with respect to 3 fixed charges, 3 fixed points. Okay, so in the case of 3 points, there is one slight difference between possibilities which we'll need. So this central point could either lie in the convex hull of this triangle or not, if my triangle would be very flat. So then I'll be in this situation like this. Oops, maybe I'll use another color for that. So this would be the point which has all 3 of them on the same distance. So let me use the color. So the difference between these two situations is that the central point, here it sits in the convex hull of my triple, and here it sits outside the convex hull of my tree. Okay. Anyway, to any configuration, you have the associated gas sheet. Okay. Sorry. Yeah, no.
Just that I like to appear on the video.
Yeah. Okay, thank you. So a Voronoi cell, as I mentioned, we fix a bunch of points, and the Voronoi cell consists of all points in the space which has exactly the same set of nearest sites. Okay. Yeah. Okay, let's see. Let me see. Okay, that's some. Let me go to the theorem, and then let me explain the theorem. Then I'll back a little bit. Okay, the theorem is as follows. So if we fix a configuration of point charges of the same sign, and assume that it's generic, I'm not going to explain what this thing is, but it's really generic. If you perturb any configuration a little bit, it will become generic. Now I'm saying that I'm looking at the family of potentials where the parameter alpha would be increasing. Yeah. So I have a family of potentials which would be the sum of my charges, psi I divided by the distance, some power alpha, I from 1 to L. So alpha would be my parameter. I'm saying that if I fix where my charges are located and what the values of the charges are, and I allow myself to increase this power alpha, then for all sufficiently large alpha, the critical points of this potential would be in one-to-one correspondence with the cells of positive codimension of the Voronoi diagram, which those fixed points produce. But I only have to count the so-called effective cells. And effective cells means that a cell is called effective. So this cell is effective. And okay, so here all 1, 2, 3, 4 cells are effective. And here these 2 cells are effective and these 2 cells are non-effective. Let me tell you what effective is. So to a cell you can associate the number of nearest sites. So those points of my configuration which are in the closest position. If the cell intersects the convex hull of those things, then it's called effective. Here, for example, so this point, its set of nearest sites is all 3 white points, and it lies in the convex hull. Here, for this point, again, these 3 points are closest to it, but it misses the convex hull. The convex hull is this white triangle here. For example, here, these 2 points are closest, and the cell itself intersects the convex hull of those 2. So we have this intersection point, and the same works for all 3 legs. Here, this line intersects that thing, which is the convex hull of its set of nearest sites, and this works well, but this does not. It misses, so it should intersect this thing to be effective, but it doesn't. So in the formulation of the theorem, I am saying that critical points would be in one-to-one correspondence for sufficiently large alpha critical points would be one-to-one correspondence with effective cells of this configuration. And you even can read the Morse index of the critical point from the codimension of the correspondent cell. And let me tell you why this is true. And the explanation is here. And the formal proof is a little bit involved, but not so complicated. It turns out that if we again fix the positions and the values of the charges and look at such a limit when alpha goes to infinity. And it turns out that it goes to this piecewise quadratic function, which is the minimum of the distances from a variable point x to the sites, to the position of the points. And here is the illustration. What happens if you increase alpha and perform such an operation? You see that the function becomes piecewise quadratic function, which is just the minimum of the distances. And such functions are rather easy to work with. And the places where such function is not smooth is exactly the Voronoi diagram of our configuration of charges. You have to do some technicalities, but at the end it's not such a difficult thing. What is surprising is our conjecture, which is numerically, we have checked it in many cases on the computer, is that even so, the theorem says that for large alpha, we have a very good control of the number of points in terms of the configuration of the Voronoi diagram. But all cases we know of, even for small alpha, the same bound works. So you can, for all alpha, at least 1/2, I remember correctly, the number of critical points of a potential is still bounded by the number of effective cells of the Voronoi diagram. And this is a surprise. We thought we'll be able to obtain a proof of these things, studying how the number of critical points behaves as a function of this parameter alpha. And at the beginning, we hope that it will behave monotonely. And then if we know the situation for large alpha, we'll be able to derive what happens for small alpha. But unfortunately, it's not true. So it could happen that when you increase alpha, some new critical points pop up and then they disappear. But again, all cases we know this, the number of cells of Voronoi diagram give the upper bound. Okay, let me give you a calculus 1 question related to this. You'll not be laughing in 2 minutes. Okay, so so there is a relative version of all this. I'll skip it. But what it boils down to is the following calculus 1 question. I'm embarrassed to admit that even the simplest case, I don't know what to do. So okay. Okay, it's as follows. So assume you have a bunch of points in the plane. You can assume that they lie in the upper half plane. It doesn't matter for. So say we have x1, y1, x2, y2, and so on, x, n, yn. Okay. Now, with this configuration, I'll form a function in one real variable. X belongs to the real axis, and which is, so here is my variable point x. So let me put dots here instead of crosses, just not to confuse you. So which is the sum of the inverses of the distances. So it's sum I from 1 to n, 1 over x I minus x squared plus y squared, yi squared. So you look at the sum of inverses, squares of the distances. Okay, that's a nice positive function. It looks like this. It decreases at infinity. And here is a big conjecture. So if I put it here, you'll not see it, yeah? Okay. 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 Okay, good. Just not to erase my picture, so conjecture. So the number of local maxima of phi of x is at most n. That's it. So I'm saying that for this function, the number of humps is at most the number of points here. It's open for n equals 3. You wouldn't believe it. It's a small piece of a much bigger conjecture, but even this thing I cannot handle. And, well, so this is equivalent to the number of real critical points. So here we have one minima in between two consecutive maxima, and it decreases to infinity. So that's equivalent to saying that the number of real critical points, the number of real critical points is at most 2n minus 1. So that's an equivalent statement. And I had master students doing numerics, I don't know, thousands of hours of experimentation, huge statistics, no proof for n equals 3. And if you just differentiate and look at the numerator here, you get a polynomial of degree 4n minus 3. Real polynomial, which for some reasons never have more than that many real roots. And this is a small piece related to this problem. I'll probably want to skip these discussions about how Maxwell conjecture fits with a piece of computer, so there is a piece of computer science is called complexity of Voronoi diagrams. So there was some famous result of Macmillan involved and so on and so on. But let me instead maybe show you what Maxwell wrote. So I have some 5 minutes. So this is more like a piece of a history of mathematics, but rather funny. So topology maybe was developed as a science, as something interesting by Poincaré in 1890s. But the word topology comes originally from a German mathematician, last name is Listing, who was a student of Gauss, one of very few students of Gauss. And he developed very funny notions which were kind of H1 of surfaces in three-dimensional space and H2, the first and the second homology, which he called a degree of cyclosis and degree of peripraxy. And I don't know how, but Maxwell apparently read those things, although he was a physicist and an engineer, and Listing was a very obscure person who published in even more obscure journals. I don't know how he came across that. And that's what Maxwell writes. So he actually develops Morse theory more or less. So he studies, so if you have a function, so in Morse theory it's typical to look at the set of where your function attains values small or equal than a given constant, and then you move this constant from minus infinity to plus infinity, and each time you hit the critical value, then the topology of this set changes, and it actually, what happens typically to this set, you glue a handle of the index which is equal to the index of this critical point, and that's what actually Maxwell says here. But as I said, Morse theory was developed 60 years after that. And he discusses all that, and he says that in such a process, if you have that many negative charges, he mentioned that if you are in the case of the three-dimensional space, your potential goes to 0 at infinity. You can actually consider a function of a three-dimensional sphere. So you can compactify the situation, and you go with the level from minus infinity, and there you see your negative charges. The potential at the negative charges goes to minus infinity, so you know what happens when your level is close to minus infinity. Then you grow up, you have at the end, when you go to plus infinity, you know what happens with your level at plus infinity. So you should get, if you have totally, he uses n for the total number of charges. I'm sorry for this confusion. So you have to get n minus 1 critical points in that way. But he also discusses the situation when your charges is not necessarily points. He says that, well, in my terminology, it's L minus 1. So if you have L charges, you should necessarily have L minus 1 critical points. But then he says, but besides that, this required number, if your charges are of any form, you can get some additional equilibrium points about which you can only say that their number should be even. And then, so here is his last phrase. So he said, if the form of the charged bodies or conductors are arbitrary, we can only assert that the number of these additional points is even. But if these are either spherical or points, then the number arising, additional number, should be at most L minus 1 times L minus 2, where L is the number of bodies. So he gets L minus 1, which is required, and then he claims that to that you should add at most L minus 1 times L minus 2, which gives us his bound L minus 1 squared. And this is a complete mystery. How the hell did he got that thing? Because people looked, and then his finally the posthumous edition of this paper was edited by Lord Kelvin, J.J. Thomson, and he added this phrase. I have not been able to find any place where this result is proved. So that's the end of the story. Thank you.